Atul sir.
Sir.
Okay sir. Sir, ಏನು ಪೂರ್ಣಪ್ರಜ್ಞಾ ಕಾಲೇಜ್ ಸರ್?
ಹೌದು, ಪೂರ್ಣಪ್ರಜ್ಞಾ ಕಾಲೇಜ್.
ಉಡುಪಿ. ಓಕೆ.
ಹೌದು, ಉಡುಪಿ. ಪೂರ್ಣಪ್ರಜ್ಞಾ ಸಿಂಗಲ್ ವರ್ಡ್.
ತುಳುವ ಸರ್ ನೀವು?
ಯಾವ ಸರ್?
ತುಳುವರ ನೀವು?
ತುಳು ಅರ್ಥ ಆಗುತ್ತೆ ಮಾತಾಡೋದಕ್ಕೆ.
ಓಕೆ ಓಕೆ ಸರಿ. ಇನ್ನೊಂದು 5-10 ನಿಮಿಷ ಸರ್, ರಮೇಶ್ ಸರ್ ಜಾಯ್ನ್ ಆಗ್ತಾರೆ.
ಸರಿ ಸರಿ.
ಇಂಟ್ರೊಡಕ್ಷನ್
ಯೂಟ್ಯೂಬ್ ಲಿಂಕ್ ಅಲ್ಲಿ ಡಾಕ್ಟರ್ ಹಾಕಿದೀರಿ ಸರ್. ಡಾಕ್ಟರ್ ಅಲ್ಲ ನಾನು. ಯೂಟ್ಯೂಬ್ ಲಿಂಕ್ ಅಲ್ಲಿ ಡಾಕ್ಟರ್ ಅಂತ ಹಾಕಿದಿರಿ.
ಪರವಾಗಿಲ್ಲ, ಅಡ್ವಾನ್ಸ್ ಆಗಿ ಒಂದು PhD ಸಿಗ್ದಂಗೆ ಆಯ್ತು. ಓಕೆನಾ ಸರ್?
ಓಕೆ ಓಕೆ.
ಸರಿ ಸರ್, ಸರಿ ಸರ್. ಯಾ, ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಓಕೆ. ಸರ್
ಹೇಳಿ ಸರ್.
ಟಾಕ್ ನಾನು ಮಿಡ್ಲ್ ಒಂಚೂರು ಕನ್ನಡ ಮಾತಾಡ್ತೀನಿ, ಬಟ್ ಹೆಚ್ಚಾಗಿ ಇಂಗ್ಲಿಷ್ ಮಾತಾಡ್ತೀನಿ.
ಪರವಾಗಿಲ್ಲ.
Dr. Atul Bhat, good afternoon.
Good afternoon, sir.
Thanks for joining us. Poornaprajna.
ಹೌದು.
Poornaprajna ನಮ್ಮ ಪ್ರಿನ್ಸಿಪಾಲ್ ಆಗಿದ್ದಾರಾ?
ಆರಾಮಾಗಿದೆ ಸರ್.
ಓಕೆ. ನಿಮ್ಮ ಕಾಲೇಜ್ ವಿಸಿಟ್ ಮಾಡಿದ್ದೀವಿ ಡಾಕ್ಟರ್.
ಹೇಳಿ ಸರ್, ಮಿಸ್ಟರ್ ಸರ್, ಡಾಕ್ಟರ್ ಆಗಿಲ್ಲ.
ಆಗ್ಲಿ ಅಂತ ಈಗಲಿಂದ ಹೇಳ್ತಾ ಇದ್ದೀನಿ. ನೀವು ಡಿಗ್ರಿ ಟೀಚ್ ಮಾಡ್ತೀರಾ PU-ಗ?
ಡಿಗ್ರಿ ಸರ್, BSc.
ಡಾಕ್ಟರ್ ರಾಘವೇಂದ್ರ ಸರ್ is
ಹೌದು
your
ಹೌದು,
principal.
he is our principal.
Yes. He was in fisheries. He was coming as a visiting faculty to Fisheries College.
Oh,
And
okay. Okay.
Good evening, everybody. We have with us Mr. Atul Bhat. He is the Assistant Professor in the Department of Physics, Poornaprajna College, Udupi. As you know, Poornaprajna College is one of the very well-known institutes in the state. Mr. Bhat has obtained his MSc in Physics from Jain University, and he has been working as an assistant professor in Physics since 2016. And he joined Poornaprajna in 2019. He is working as coordinator of Poornaprajna Amateur Astronomers Club and is involved in astronomy outreach activities and popularization of astronomy. Mr. Bhat has published papers in peer-reviewed journals and also present in international conferences. And today, Mr. Bhat will be delivering a talk on rotational mechanics. I'm sure participants will be highly benefited by this talk. Mr. Bhat also have become the YouTube platform, which will be live streamed. Hello. Friends have joined on YouTube platform also. They will be happy to listen to you. Now I request you to deliver your talk on rotations and results. Over to you, Doctor.
Thank you. Thank you. I hope I'm audible. My presentation.
Yeah, you are audible.
But sir, hello.
Yes, sir.
Sir, ನಿಮ್ಮ ಕ್ಯಾಮೆರಾ ಆಫ್ ಮಾಡಿ, ಯಾಕಂದ್ರೆ ನಿಮ್ಮ ನೆಟ್ವರ್ಕ್ ಪ್ರಾಬ್ಲಮ್ ಇದೆ.
Okay.
No. You stop.
Okay, fine. Yeah. I hope the network is clear now. I've just switched the network. Okay. Good afternoon, everyone. Today I'll be speaking on this topic called rotations and results, because when I say rotational mechanics, it's a very broad topic. And many of the objects we see in daily life, the things that we learn from school, rotation is involved in every aspect of it. In school, we are told about the solar system, the planets. Chandra Bhumi Sutta Tirta Irtane, Bhumi Suryan Sutta Tirta Irtane anta heltivi. Again, inside the atoms, we've got electrons going around the nucleus. So now ಮನೆಯಿಂದ ಶಾಲೆಗೆ ಹೋಗ್ತಾ ಬಸ್ಸಲ್ಲಿ ಹೋಗ್ತೀವಿ, ಬಸ್ಸಿಗೆ ಒಂದು ಚಕ್ರ ಇರುತ್ತೆ, ಅದು ತಿರುಗ್ತಾ ಇರುತ್ತೆ. So rotation is a very important aspect of our daily lives. It is something we learn from younger ages, and even today when we learn advanced physics, we prefer doing calculations with rotational variables. Now coordinate system anne change ಮಾಡ್ತೀವಿ. This is in higher studies. So rotation is something that we deal with on a day-to-day basis. So I would like to speak on this topic today, and I am just here to introduce you to the basics of the physics involved in rotational bodies. So whenever a body is going in a circular path, it is rotating, or a wheel itself is rotating. What is the physics involved, and how can we apply some of these aspects to our daily life? So these are the things I'll be covering today. So whenever I say rotational mechanics or rotations, this is something that we see. We always know this, that rotation means basically it is going in a circular path. So we know there is a radius to this, and this radius is measured from one point, which we call the origin. Now an object that is going around, right? So that is covering 360 degrees is something that we all know. But we'll also notice that whenever there's an object is closer to this origin, it is covering the smaller circle when it's completing this 360 degrees. You can see this in this image here. The blue dot particle is going on a larger circle, and the pink dot is going in a smaller circle, and both are going at the same speed for our eyes, and you can see both are covering 360 degrees at the same time. Yet the physics of these two objects are pretty much similar, at the same time very different. It is all the game of numbers, but the variables, the formulas, they are all the same. So let's understand rotational mechanics, but before we understand rotational mechanics, we need to know a little bit about linear motion, right? So when we learn physics after units and dimensions, the first thing we learn is motion in one dimension, the linear motion. So I'm not going to touch this topic in detail, but we all know this. When an object is moving in a straight line, we know that it starts from one point and it reaches another point, and this distance covered, we call it displacement, because distance is a scalar. Whenever there's a curved path, then we call it the distance, the total distance covered. But when an object moves from point A to point B, the shortest distance between these 2 points is known as displacement. So we can break down a distance into smaller parts, into displacement, and so on and so forth. And then, yeah, so whenever we have displacement involved, we also have velocity, which can be calculated. So displacement leads to velocity. So whenever displacement changes with respect to time, we have got velocity. We measure this as dx by dt, or delta x by delta t, which is given as v. Once velocity is not constant, velocity is also increasing, then we know it is known as dv by dt, the rate of change of velocity, which is known as acceleration. This is the second differentiation, or d square x by dt squared of this same x, and that is acceleration. Then we have this wonderful concept called momentum. Momentum is very important because it basically tells me that if I am supposed to collide with something, then how much velocity will I impart into that object? That is known as momentum. We usually define this as the product of mass and velocity. No, it is basically how much of my energy or how much of my velocity will be transferred into the object that I or collide. That is momentum. So if my mass is high and velocity is low, I can say momentum is high. But if my mass is very low but velocity is very high, even then my momentum is very high. So it's a game of that mass and velocity. Both of these numbers matter. Then when we know momentum, again, like I told you, when displacement changes, we get velocity. Similarly, when momentum changes, we have something known as the force. This is given by Newton's second law, rate of change of momentum. Right? Oh, I made a mistake over here. This is dp by dt, and we get dmv by dt, or yeah. So ma, f is equal to ma is what we get. A small error in this equation here, but anyways. So f is equal to ma is a well-known equation to us, very much a well-known equation to us. Newton's second law, rate of change of momentum is directly proportional to force and takes place in the same direction as the force. So this is a very beautiful law, and we are all familiar with this. If you learn physics even a little in your life, you'll learn this. But whenever we move in circular motion, then these things, will they remain the same or not? That is what we have to find out. So when we know these linear motion variables, the properties, then we have these equations, right? So acceleration is given by dv by dt. So dv means what? It's basically change in velocity. So I can write it as my final velocity minus initial velocity. Instead of putting this vf, vi, ve, whatever, I will put v and u, where v is my final velocity, u is my initial velocity. So v minus u by t is still acceleration. Now, if I cross multiply and do some math, I will get one equation, which we call the first equation of motion, that is v is equal to u plus at. We are all very familiar with this. Similarly, after an object covers a distance of some meters or centimeters or whatever it is, we can calculate that distance by knowing it's the initial velocity and the acceleration it goes through. So s is equal to ut plus half at square is also a very familiar equation to all of us. Similarly, the third equation of motion, which is v squared minus u squared is equal to 2as. This is also a very famous equation that we have all calculated and worked with. So these are three equations of motion that we can write for any linear motion. So slowly, before we jump into rotational motion, we will first understand one very important concept known as pi. In school, in geometry, we are taught that pi is basically the ratio of circumference to diameter. So c by d is equal to pi. We also know that diameter is equal to 2 pi, and diameter is equal to 2 times the radius, so 2r. So you get c is equal to 2 pi r, and this is the formula for circumference. So this value of pi that we use, that comes from this ratio. And for any given circle, this value of pi is basically 3.14 is what we approximate it to be, but it's a very non-ending number. right? So 22 by 7 is a good approximation. So pi is something known to us. So we're using pi a lot. Now, when I spoke about linear motion, I spoke about displacement. Now, when I'm talking about circular motion, then I will talk about angular displacement. So circular motion means what? Basically, the path of the object is a circle, right? So path of the object is a circle, and it is fixed from this origin point, and it is going around that point. It is not going away from that point yet. When we say circular motion, it is going around that point. So it is going to cover an angle, right? It's not going to cover a distance in linear way. It is going to cover a angular distance. So we call it angular displacement, right? So angular displacement, if I'm supposed to deduce it or calculate it, basically I define it as the angle subtended by an object as it moves along a circular path. So in the red triangle that I'm showing you here in the image, I have the radius r, and let's say the distance covered by the object from this point over here to this point over here, that is s, right? And if this triangle is very small, for a very small angle theta, then this s will almost be a straight line. So if you bring this radius over to here, somewhere here, it's almost a straight line. So from there we approximate, of course, from the triangle we have got sine theta is equal to s by r, okay? And I am exaggerating the angle here to show the image for you, but this angle is very small. We treat it very small angle. So we've got sine theta is equal to s by r, right? And we call this theta as the angular displacement. So for a very small angle, very small angle, we know sine theta is equal to theta. So simply I'll write it as theta is equal to s by r, right? So now theta is the angle subtended, or if an object is moving from this point to this point, then it is subtending an angle of theta over here. And we'll call this almost an arc that is formed here. We'll call this as S, the displacement, the angular displacement. But I told you, depending upon the radius, here this distance that it goes is very large. But if the object is over here, for the same angle, it's doing a very small distance, right? So when we are talking about circular motion and a fixed radius, I'm really not bothered about how big is the distance. I'm only concerned about the angular displacement. So from here to here, to move from here to here, what is the angle it covers? That is theta, right? So if I know theta is equal to s by r, then we know that very famous equation, s is equal to r theta. So once we know s is equal to r theta, we'll also come across this concept known as radian, because this angle theta is usually given in the form of radian. In school, whenever we are measuring angles, we basically measure theta in degrees, right? So, but whenever we measure this, use this formula, s is equal to r theta, or whenever we measure this angular displacement, it is usually in radians. Now, to define a radian, it is basically an angle, right? It's an angle where the arc subtended, which I just showed you, the arc subtended is equal to the radius of the circle itself. So what you saw in the previous diagram there, that S arc that is there, that is equal to the radius itself. So if I do this calculation, what will happen? Then I know S is equal to r theta. So I'll put S is equal to r only over there. Now I'll get r is equal to r theta. So this theta is my 1 radian. So 1 radian is defined as the angle subtended by an object which moves a distance that is equal to the radius of the circular path, right? So theta is equal to 1 radian, right? So when s is equal to the circumference of the circle, right? If I say the entire distance covered by the object in the circular path is the circumference, then I'll put s is equal to c. So I've got c is equal to r theta, right? And I know that when it goes around a complete path, the angle it covers, right, that I'll take it as 2 pi. So that is what gives me theta is equal to 2 pi for the entire circumference. So we know 2 pi r is the circumference formula. So from there I got this relation. So now I know that theta is equal to 2 pi. 360 degree, because it's for only for the circumference case, 360 degree is equal to 2 pi, right? And that means pi is equal to 180 degrees. So whenever I say pi radians, I mean 180 degrees. And this is what we usually have in all of these rotational diagrams. So this is a small animation that I've got that shows you basically what a radian is. So whenever you take this this distance subtended by here, let me just play it again. I hope, please. Yeah. So let's say this radius, this same radius distance, whatever I have, that much I will cover in distance over here. Somewhere this much is equal to the radius, right? So when I get this, yeah. So you see that the radius is converted into this distance. Now this angle is 1 radian. Okay. So once we have angular displacement, once we've sorted radians, once we've got the value of pi, then we'll move on to the change of angular displacement, that is angular velocity. Just like your linear movements, in linear displacement, whenever it changes, I had linear velocity. Same way, angular displacement, whenever it changes, I've got angular velocity. So I can call this as rate of change of angular displacement. And this is given by the formula d theta by dt. So V rotational displacement, okay, angular displacement is equal to rate of change of angular displacement. So in the earlier case, I had V is equal to dx by dt, where x was the displacement. Here theta is the displacement, so I've got d theta by dt. And instead of writing V rotational every single time, I'll write it as omega, right? So let's use the Greek symbol omega. So omega is going to be by angular velocity. So angular velocity is d theta by dt. Now s is equal to r theta, so I've got theta is equal to s by r. So I'll just take the r outside the differentiation because r is not going to change. It's a circular motion, radius is a constant. So r is not going to be differentiated. I'm going to, if I apply the product rule also, I'm going to get dr by dt as 0. So I have this product rule result over here, 1 by r ds by dt, right? So I'll take the r onto the other side, and on the left hand side, I'll have r omega, and on the right hand side, I've got ds by dt. Now S is the distance or the displacement covered there. So ds by dt is the rate of change of displacement, the linear displacement, which is nothing but velocity, right? So ds by dt is velocity, and that I'm getting is equal to r omega. So I can write V is equal to r omega. Now, this is a very beautiful formula that relates your linear velocity here. V is the linear velocity, and that is related to the angular velocity, right? So if you know the linear velocity, you can always calculate the angular velocity. You just simply divide it by r, and this is how we get this. Okay, so the diagram on the right side will show this pictorially better. Let's talk about directions here because these are all vectors. Although I have simply shown you v is equal to r omega, this is a vector over here. Everything is a vector. Now, when I'm talking about circles, circular motion, all of us have learned vector is basically a straight line. Vector is from one point to another, it's always pointing in one direction. We define vector as a physical quantity that has a magnitude and a direction. So when I'm talking about circular path, it's always constantly changing direction. Once it's here, once it's here, once it's here. So it's changing direction continuously. So how do I define it in vector form? Of course, my radius vector is always pointed from the origin towards the circumference. Then I've got the velocity vector, which is usually tangential. Not usually, it's always tangential to the circular path. And I've got r and v are my two vectors, right? So I can write this product v is equal to r omega as a vector product, and this vector product we call it a cross product. So because omega is a vector and r is a vector, and the result is going to be velocity, which is also a vector, I'm getting a cross product. Cross product is basically omega cross r. Now, by the definition of this cross product, I know that whenever I have A cross B is equal to C, I've got A cross B is equal to C, then C is always perpendicular to both A as well as B. So here I've got omega and R. So let me draw it again for you. I've got V. Okay. I can just take it from the other side and do the same calculation. Doesn't really matter. So if let's say if V is my result, right? V is the result. V is equal to omega cross R. So V is the result, and that is my vector in one direction. And now R is also this vector, right? Then omega cross R is going to give me the V vector such that V is perpendicular to omega, V is perpendicular to R. In this particular case, where velocity is constantly changing direction along the circular path, radius is usually from the origin, it is always pointing at the circle. Then omega is perpendicular to both V as well as R, and that is a vertical direction. This is very beautiful. Whenever we say circular motion, direction, linear motion, we know the direction is very integral. But whenever we say circular motion, whenever something is going round and round, then that can also be shown as a vector, but the vector is basically perpendicular to the plane of circle or orbit, right? So the example I've given here is a top. So you can have a top, or if you're from my generation, you'll have heard of something known as Beyblade, or today you'll get fidget spinners. So whenever something is spinning, then omega is perpendicular to the orbital plane. That is what we call it, right? So whenever we have multiple rotations, then we define frequency as one term, which is basically the number of rotations per second. Whenever something is spinning very fast, the fan is going very fast, then we have multiple rotations. Then I need a quantity known as frequency, which says frequency is equal to the number of rotations per second, right? So frequency is directly proportional to angular velocity. Because velocity is fast, then more number of rotations will be happening per second. And this relation is given as F is equal to 1 by 2 pi omega. Or I can always write omega as 2 pi times frequency. And we also call this omega as angular frequency. Whenever there is frequency involved, we call omega as angular frequency, right? So this is a better picture here. So whenever there is an object moving from here to here, there is an omega, right, angular velocity, and number of times it rotates per second, that is given by f. So if you know omega, you can simply calculate how many times it will go around in a second. And whenever we have got frequency involved, we have got period. Period is basically the time taken for one rotation. So frequency is number of rotations in 1 second. Period means how many seconds for one rotation. So just by the definition itself, you can make out that it is going to be a inverse rule, right? So if you know frequency, then you can calculate T as 1 by frequency. Or if you know T, you can calculate frequency as 1 by T. So this relation is always realized. So you all know this. Now coming into circular motion. So whenever something is rolling, there are two types of motion in it. So one, we have the circle, the wheel that is actually going round. Wherever it is going round like this, right? It's the rotational motion. And then the wheel also moves forward when it is going forward. Okay. So there is a forward motion which we call as translation motion, and then the circular motion. When you combine, the wheel rolls. Right? So when the wheel is rolling forward, of course, this point here is going forward. And we know this point here is going backward. And this point here is going nowhere. So whenever the wheel is rolling, this center is not moving anywhere. But when the entire wheel is moving forward, this point is moving forward, this point is moving forward, and the center is moving forward. So I can write the velocity at the middle, the center, is nothing but simple forward motion, linear forward motion. This is translational velocity. There is no rolling happening at the center here. Nothing is moving over here at the center. So it is plus 0. So it is simply VR. Okay, sorry, this is VT. Okay, this is VT. When we talk about the velocity at the top of the wheel, at this point over here, then velocity is nothing but the wheels part that is here, that is going forward, that is the translational motion, as well as the rotational motion, as well as the wheel is completely moving forward together, that is a translational motion. So at this point, this particular point is not only moving forward with the wheel, it is also moving forward due to the rotation. So we've got velocity at this point here as Vt plus Vr. And at the base, similarly, you can make out that the wheels, this part here, due to rolling is going back, and due to translation is going forward. So they cancel each other, and the velocity here will be 0. And it is only when the velocity at the base is 0, we can say the wheel is rolling. Because if the velocity is not 0, if translational motion is greater than the rotating motion, then you know it is skidding forward. Right? And if the translation motion is not high enough and the rotational motion is very fast, then the wheel will basically rotate wherever it is standing. So this usually happens when our vehicles, when we suddenly accelerate it, what happens? The wheel, wherever it is standing, the vehicle is not going to go forward. The wheel itself is going to go rotate very fast. Or you can hold the brake and give an acceleration. You see the wheel is rotating very fast, but it's not moving forward, right? In which case, the wheel is not going to roll. It is just going to be rotating, right? So these are the relations. And then angular acceleration, because we spoke of angular velocity. What is angular acceleration? Of course, rate of change of angular velocity. We'll call this alpha. Okay, for a single set, we'll call this alpha. So angular rotation, the rate of change of angular velocity, d omega by dt, is equal to alpha. Fine. So now omega is nothing but V by R, which we just deduced a while ago. So omega is equal to V by R. If I find d omega by dt, I get d by dt of V by R, which is equal to alpha. Again, here the radius does not change. I'll bring it out of the differentiation and I write it as 1 by R into dV by dt, right? And taking it to the left hand side, the R, the denominator here, if I take it to the left hand side, I'll get R into alpha is equal to dV by dt. Again, V is the translational velocity, the linear velocity. And when rate of change of linear velocity is involved, we know there is linear acceleration. So this here term, the linear velocity rate of change becomes linear acceleration. So I can write R alpha is equal to A. That's what I've written. A is equal to R. So now if you know the angular acceleration alpha, then you naturally know what is the acceleration of the wheel in translational motion, or the tangential acceleration. So these are all small formulas that we'll be using further. Right? As such, you will not in daily life you will not be able to measure these things very easily. You need apparatus and devices to measure these things, but these are the relations. So let's talk about direction again. I told you angular velocity is perpendicular. So let's talk about angular acceleration. Again, I told you acceleration here, A, linear acceleration is a vector, R is a vector, so alpha is going to be a vector. And when product of two things will give me the as a vector itself, I'm going to take a vector product or a cross product. Just like the previous case, I know if alpha is a vector and R is a vector, I know A is going to be perpendicular to both alpha and R. Or if I write this result over here, I know for sure that this alpha is going to be perpendicular to both A as well as R. So this is something we know, right? So again, I know what is my radius vector. I know my acceleration vector. So I'll just write it in this form. Acceleration vector again is change of velocity here. So change of velocity, velocity increases. You see the vector size just increased. Let's say the light green vector here is initial velocity, and then the dark green vector is the extended velocity, which is the final velocity. And whenever velocity increases, angular velocity increases, right? And the change of velocity is along this direction. Of course, you can make out from this dark greens over here. And change in velocity is nothing but acceleration. Omega is this vertical vector which I had shown you earlier. But when the velocity increases to final velocity, omega will also change to omega f. So final angular velocity. So velocity, angular velocity changes, and this is also along this up direction, and now this is equal to alpha. So now you can very clearly see that A vector, R vector, and alpha vector, they are all perpendicular. A and R need not be perpendicular. A and R need not be perpendicular, but if you have A in one direction and R in one direction, then alpha is perpendicular to both of these, right? So again, just like your angular velocity, angular acceleration is also pointing upwards, right? So this is the vector directions involved in circular motion. Now we had equations of motion, right? We had V is equal to U plus AT. Now what happens? Again, V is linear velocity. So angular velocity, I'll replace it with U is linear velocity, initial linear velocity. I'll replace it with initial angular velocity. I've got linear acceleration A over here. I'll replace it with angular acceleration. So I'll get omega f is equal to omega I plus alpha into t. I missed a small t over there, so let me write it for you. It's equal to into t, right? So in your books, you'll find this as omega is equal to omega naught plus alpha t. That's fine. However you want to label it, as long as you label it right. Similarly, the second equation, S is equal to ut plus half at squared. What happens to that? S is displacement, so I'll replace it with angular displacement. U is velocity, I'll replace it with angular velocity. A is acceleration, replace it with angular acceleration. Then I'll get theta is equal to omega I, right? Initial velocity, omega I into t plus half alpha t squared. Again, alpha here, not A, alpha t squared. So the equations of motion can also be defined in rotational terms. Let's look at the last equation over here. We've got v squared is equal to u squared plus 2as. V squared, again, velocity squared, replace it with angular velocity. U squared, replace it with angular velocity here. And A, replace it with acceleration, angular acceleration. S is displacement, angular displacement. I'll get this entire term over here, which is omega f minus, omega f squared is equal to omega I squared plus 2 theta, through alpha theta, right? So your linear motion equations can also be written as angular equations. There are angular equivalent. It is not the same equation, it is an equivalent. right? So let's talk about mass. We've spoken about length, spoken about velocity, acceleration. What about mass? Now, here is a small deviation from the intuitive point of it. Whenever we talk about mass, whenever we talk about an object rotating, then the entire mass of the object is rotating. Now, mass means basically it is made up, an object or matter is made up of atoms. So I can say the entire mass is equal to mass of individual atoms or individual sections or individual particles or whatever it is, right? So mass is distributed. So when I say rotating mass, I need to consider that distribution as well. And I define a term known as the moment of inertia, which is given by the formula mr squared, right? And moment of inertia, I can call it an equivalent of linear mass, right? You can ask me, sir, there's a mass term along with radius over here. No, that is fine. When I'm talking about rotational motion, the equivalent, rotational equivalent of mass is moment of inertia. Inertia is basically laziness. Any object, of course, Newton's first law, any object will continue to be remain in the state of rest or of uniform motion until and unless acted upon by an external force, which means unless pushed or stopped, applied force on, the object will either remain at rest or keep moving forward. So that is basically going to be defined because of mass itself. If something is moving, something is pushed, then that mass will have an inertia and is going to go forward. So when I'm talking about rotational motion, we talk about moment of inertia. So I told you any object can be, we can make it into smaller masses combined together. Okay. So let's say this is one region here. This entire region here has some mass m, which may be result of the summation of these three masses or the adding up of these three masses, right? Or there may be 100 masses like this, 1,000 masses like this, or all the atoms. It depends upon the distribution. And each of these mass may be located at some distance, right? The labels used here is R itself, but you can see this is a smaller vector here and the mass is larger over here. Whereas this vector is very long, but it is smaller mass. This is in between these two. So each of these particles or sections may have different mass, and each of these particles or sections may be located at different distance from the axis of rotation. So that is very important. And from there, we define moment of inertia like this. So mr squared is a direct formula, but it is basically an integration of r squared over dm. Right? You do the integration of dm will be nothing but m itself. So moment of inertia is defined like this. And the reason this is important is because moment of inertia, unlike mass, depends upon what axis you are rotating it from. Okay, so because you can see here, whenever this cylinder here is rotated along this axis, then its moment of inertia. Excuse me, what happened? Okay, I think my network is breaking. Yeah, is it fine now? Okay, let me just check my network. Yeah, fine. So this cylinder that is rotating along this axis over here, it has a moment of inertia 1 by 2 mr squared. Whereas if it, yeah. So if you take the cylinder rotating along this axis, which is passing through the perpendicular, parallel to this plane over here, then its moment of inertia is 1 by 4 mr squared plus 1 by 12 ml squared, and so on and so forth. This ring over here along this axis, it has some moment of inertia. This same ring along this axis has another moment of inertia. So moment of inertia depends upon which axis is used for the rotation, and that is why we cannot directly call it some mass. Okay, it is basically the distribution of mass that is being an equivalent here. And this is also very important because this I is going to be contributing to my angular momentum. So what is angular momentum? Just like linear velocity, there was an equivalent angular velocity. Of course, there's a linear momentum for any object moving. There has to be an angular momentum. There is linear velocity for even a circular object, right? So whenever an object is moving in a circle, is there a problem?
And chimp-human
Hello?
genomes revealed that they differ only by 1.2.
Okay. Is it audible now? ಕೇಳ್ತಾ ಇದೆಯಾ sir?
ಹೌದು ಸರ್ ಕೇಳಿಸ್ತಾ ಇದೆ, ಕಂಟಿನ್ಯೂ ಮಾಡಿ ಸರ್ ಪ್ಲೀಸ್. ಹಲೋ,
Okay.
ಕಂಟಿನ್ಯೂ ಮಾಡಿ ಸರ್, ಕೇಳಿಸ್ತಾ ಇದೆ.
Is it audible now?
ಎಸ್ ಸರ್, ಯು ಆರ್ ಆಡಿಬಲ್.
Fine. So let me just repeat it again. Whenever I have linear velocity, I've got linear velocity, then linear velocity means there is going to be a momentum, linear momentum. And we know linear momentum is equal to P is equal to mv, right? So whenever there was a linear velocity, v, there was angular velocity as well. I just showed you. V is equal to r omega. So same way, whenever I have linear velocity, I've got linear momentum, then there has to be an angular momentum associated. So angular momentum, I'll write it as L, and this is given as the product of the mass equivalent of rotation and angular velocity. We've got the mass equivalent of rotation and angular velocity. It's nothing but I into omega. Right? So here again, I is not a vector here, only omega is a vector. Okay, so if I am supposed to write I told you I is equal to mr squared and omega is equal to v by r. So now I've got mr squared v by r. This is my formula for L. Or you can see here r squared and r, these two, there's a cancellation here. This r will cancel with this 2r over here. So 1r will remain. So I can write L is equal to mvr. Right? So again, let's talk about directions. So when I'm talking about directions here, I've got L is equal to mvr. I'm not, again, mvr, I am not specifying the vector there, but r and v are both vectors. So this is going to be a cross product. Why is it a cross product? Because L is also a vector. So product of two vectors is going to give me another vector. It's a cross product. So I've got L is equal to m into r cross v, right? So let's use the top again. I've got the r vector, I've got the v vector. Then L is going to be perpendicular to both v and r. So just like your omega, L is going to be in the same direction, right? So then, just to give you an idea, whenever we are taking perpendicular, this is simple. You just take the direction of rotation as your 4 fingers. Hold the thumbs up, and if the 4 fingers are the direction of rotation, then the thumb is going to be the direction of angular momentum, or even omega, right? Angular momentum or omega both are pointed by your thumb, as long as the 4 fingers are pointing towards the direction of rotation, right? Same is also used in electricity. Whenever we say magnetic field and electric field are related, okay, direction of the current is going to give me the magnetic field. It's because these are cross products. So this is how it's used. Now, whenever I'm talking about momentum, there's going to be conservation. I know there's a conservation of linear momentum. So I've got m1 v1 is equal to m2 v2, right? Or m1 v1 plus m2 v2 when there are two objects. M1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2. We have all learned this very easily. Linear momentum is always conserved unless and until there is an external force applied. So when f is equal to 0, dp by dt is equal to 0, p is equal to constant. We've all learned this enough number of times. What about angular momentum? Whenever an object is rotating, then its initial angular momentum is always equal to final angular momentum. Right? This is m, because m is not changing. Whenever an object is rotating, m may not change. So v1 r1 is equal to m into v2 r2. So when tau, okay, I'm going to tell you what tau is. Let's call it angular force now. Is equal to 0, then dl by dt is equal to 0. L is a constant. Do we see this in daily life? This is very beautiful. We see this in everyday life. Right? When I say mvr is equal to constant, do I use this in everyday life? Yes. We've come across something known as a gyroscope. Now, gyroscope is basically a device that is going to conserve angular momentum. I'll show a small video over here. This is a video from the International Space Station where he's using a gyroscope and he's just tumbling it over. And you see the gyroscope is randomly rotating based upon how he pushes it. But now what he does, in the center of the gyroscope, there's a disc and he'll rotate that disc. And when he rotates that disc, you will see that no matter how many times he touches or disturbs the gyroscope is always going to point towards the same direction. This is very important because when we talk about linear momentum conservation, everything is going in the same direction, along the same line, right? We say m1 v1, m2 v2, and so on. They're always along one line. One object comes and collides with another object, it will move in the same line or whatever it is. But when we talk about angular momentum, something is rotating, then there is a direction to that momentum or velocity which is perpendicular. Sorry. And when I say angular momentum is conserved, then what is happening? That direction is also conserved, not simply the value. That direction is also conserved. That is why when he moved this gyroscope, initially it was not rotating, so there was no rotation, right? There was no rotation. And because there was no rotation, the direction, there was no need to be conserved. But the moment he gave it a rotation, then there was an angular momentum into this gyroscope, and then that rotation, which is pointing upwards, is conserved. Okay, this video has been going viral recently on Instagram, and this is very much useful because in space there is no north, there is no south. So to know directions, spaceships are fitted with gyroscopes. Right. Similarly, MotoGP, this is very famous photos. We find it in notebooks today. When we buy notebooks, there are beautiful photos on them. Many of them contain such images, or you can see such videos where the bike, the rider is bending the bike to very close to the ground, yet he is not falling. Why? Because the wheel is very broad, right? The wheel is very broad, the radius is very large, and he's going so fast that the velocity is very much high. And that means the angular momentum is very high. So now we can see that the angular momentum is a very large vector in this direction. And when he bends the bike, he'll basically slowly put some force to change this direction. And when he's not pushing it anymore, this direction will be conserved. So even if gravity is pulling on him downwards, right, he should fall at this point. If you do this with your vehicle normally on a normal road, you're not going to be able to ride like this. You're going to fall down because your velocity is small. So gravity will easily pull you down. But in this case, where it's going very fast, velocity is very high, angular momentum is very large, and this is going to be conserved. And this guy, even though he's pulled down by gravity, gravity cannot change the direction of this vector. So even the direction of the vector is conserved, hence angular momentum is conserved. So this is another image. Again, here the angular momentum is in this direction. He's not falling. Even though he's touching the ground, he's not falling down. Right? So this is a conservation of angular momentum. This is another beautiful toy that can be used to demonstrate angular momentum. You can see here what he's doing is basically pulling the thread and making its radius small, right? And what you observe when the radius becomes small, when the radius becomes small, the object is spinning very fast. He did not push the object to go fast. He just made its radius small. But you know here, L is going to be a constant. Mass is going to be a constant because nothing fell out of this. Mass is the same. So naturally, when radius decreases, radius goes down, velocity has to go up and it has to conserve the angular momentum. So when radius goes down, velocity goes up. If radius goes up or radius becomes larger, velocity becomes slower. So that also you can observe. When he releases that thread and makes the radius very large, you see the velocity becomes slow. You see the object going slowly rotating, right? Let's see another example. Ice skaters. Ice skaters are very popular when it comes to angular momentum. We always give this example. Why? Because they can rotate on this icy surface, and it is a part of their routine when they compete that they go around in circles. This is also true with the ballet dancers, right? The ballerinas. They also have movements in their dance where they have to rotate like this. And when they rotate, what they do is they spread their hands. You can see here, she's spreading her hand and her leg far away from her body, and she's rotating at some speed. And then slowly she'll bring her leg close to the body. She'll bring her hands close to the body. And naturally, this radius decreases. And when radius decreases, velocity increases by a large amount. And you see she's spinning very fast when she is holding her hands. So angular momentum conservation is used in day-to-day life. And the vector form is very useful. Angular momentum, I told you, comes from the change of angular force. So let's see what is angular force. It is nothing but the force required to cause the rotation. And we call this as torque. Tau is the symbol. And again, the rate of change of angular momentum gives me angular force, right? This is not supposed to be F. This is F rotational. So I will call it tau. Because F is linear force. So I'll not use the symbol again. I will replace it with tau. So this is my torque, which is known as rate of change of angular momentum. And rate of change of angular momentum means angular momentum, this form I put over here, L is equal to m into r cross v. Mass is not going to change. Mass is not going to change. Radius is not going to change. So ultimately I'll get mr into dv by dt, and v is my linear velocity. So v being my linear velocity, rate of change of linear velocity is going to give me acceleration. So I've got tau is equal to m into r into a. This is my torque, angular force. And you see m into a is nothing but force, linear force. F is equal to ma. So F is equal to ma can be substituted here, and I get tau is equal to R into F. Again, talking about the directions using the same torque. Now I've got tau is equal to R cross F. Then by now you all know this is going to be perpendicular to both R and F, right? So velocity is in one direction, acceleration, when velocity changes, we've got acceleration, and when acceleration is there, we know there is force. So force is this green vector here. And R is the radial vector. So, you know, angular momentum is perpendicular to this plane. Similarly, change in angular momentum is going to be along this plane, and hence tau is perpendicular to the plane of rotation. Right? So this is tau. Where do we apply torque? Can you use this in daily life? Yes, of course. All the spanners and wrenches that you see, they really have long arms, right? You have very long arms, right? You've got very long arms for a spanner. So why is that so? Because when you need to rotate a nut or a bolt over here, you can hold it as far as away possible, so that you're increasing the radius of rotation. Yeah.
We are using now.
Okay. So when I have the radius being very large, of course this tau is equal to
That
R. Is there a problem?
fine.
Okay. Now let me just switch up.
You can find
When we have,
yeah.
okay. So when we have a spanner, okay. When we have
this is the most advanced part of mathematics. We are first this is called Taylor treatments. So now till now the concept is
I
one
think
to all.
some videos being shared
Now
on
the concept is this because of bioinformatics. Now because
yeah, there is some audio coming on to me. I can hear some audio. Can you please disable it?
One individual, maybe it is not good for another individual. That's because
anyways, let me
there is
just
a
continue.
change.
So we've got torque, and torque comes from this radius into F. Right? So whenever I've got a wrench or a spanner, then this increased radius
Already
will be higher torque. So I increase R, then the range can be really long, and this rotational radius becomes large. And when radius becomes large, even if my force is very, very, very small, my torque can be very, very, very large. This is why your spanners usually come as a very long devices. Right? Another example I can give of application of torque is this quote, right? We have this quote by Archimedes which says that, give me a lever long enough, fulcrum strong enough, and I'll be able to move the world. Right? Excuse me, I'm getting some audio onto this channel.
Problems. Especially this is going to may help in cancer patients. So this is a new advanced area. Of course, it is
Archimedes was the one who said that, give me a lever long enough and a fulcrum strong enough, then I can move the world. What did he mean by this? He was basically talking about torque. Because if I take a very long lever, and if I put an earth on one side of that lever, right, the lever needs to be really long. Then if it is really long lever, then this radius is very large. And this side, because the radius is very large, if Archimedes simply stands on this, then the torque is going to be very large. And here you see the earth is on this side and the radius is small. So when the torque is very large here, that equivalent torque will be able to lift the earth from this point. So this is what Archimedes said when he said, give me a lever really long and I can lift the world. But a very common daily life example of torque is on our doors. Every day we open so many doors in our daily lives, and you see that every single time when we open the door, the handle for the door is always on the opposite side of the connected side, right? So you've got a door's hinges, and the handle is always away from that hinge. Why? Because you've got a radius, right? And if this radius is really large, then small force will be able to open the door. If you try to open a door with the hinges, you can try to open a door with the hinges. We can do this with our windows. Whenever we try to close a window, we hold at the hinges and pull it in. And when that happens, what happens is basically we are facing a lot of difficulty to close the door. So when the force I need to apply, or the torque I need, and has to be attained from a small radius, I need to apply a very large force. But if the radius is large enough, the force can be very small. So I can simply push the small force and the window will open. Right? Another example of torque is basically our gears. Whenever we have a car or a bike, we talk about gears. Inside our car or a bike, what is happening? The engine has a wheel, right? A shaft, we call it. The piston is going to push this wheel, and this wheel is always going to go in one rotational speed. But when I want more power, then I will connect this wheel with a bigger wheel over here. And when I connect it with the bigger wheel, what happens? The radius increases. And when the radius increases, torque will also increase. If I want to go on a higher gear, right? When I go on a higher gear, then I will change the lever to another radius like this, and the same engine, same rotation now is transferred to a larger rotation. And because the rotation is large, the torque is going to be really large. Right? So the bigger the wheel, the more the torque. The smaller the wheel, the faster the engine will move. Right? So torque is used in our day-to-day life just because of this one quality, that when force is very small, if radius is large enough, torque can be large. Right? Now let's talk about circular motion. Right? Whenever something is moving in circles, okay, we'll stop talking about spinning. We'll talk about an object moving in a circle. Then let's simply draw this vectors again. I've got V and VB as the vectors here. Let me simply redraw this. You know, vectors can always be redrawn as long as their magnitude and directions are constant. So I've got VA vector and the VB vector. Let's move the VB vector to meet them here. Then by the law of triangle of vectors, I'll get the resultant vector here. Okay. You can move this vector. In some cases, you'll move this VB vector over here and you'll get the same result ultimately. You'll see that the resultant vector is downwards, right? Which means whenever we have a VA vector here and VB vector here, I can find the resultant vector. Now let me call this change in velocity vector as delta V. Of course, velocity, when I'm saying an object is moving in circular motion with uniform velocity, the velocity may be equal. It is not accelerating, it is velocity is equal, right? So I can say VA is equal to VB is equal to V, but the vectors are not equal because the directions are completely different. So VA vector is not equal to VB vector. So now I've got the VA vector and the VB vector, I've got the delta V vector, which is the resultant vector, right? And from these two, this triangle over here, this triangle over here, and this triangle over here, you can take them to be equal, right? And you'll get that this distance over here is the arc S, which is similar to this distance over here, right? This distance over here, which is delta V. And the velocity vector here is nothing but the radius vector, the equivalent, so S by R. And if I equate this, I will get delta V by V is equal to V delta T by R, right? Or equate them together, I'll get delta V by delta T is equal to V squared over R. Delta V by delta T is nothing but acceleration. And now I've got an acceleration that is pointing inwards, downwards, and that is known as centripetal acceleration. So whenever an object is going in a circular path, it is always going to have a force acting towards the center, and this is known as centripetal acceleration. And that value is given by the velocity squared divided by radius. Okay, so if an object is moving very fast, velocity is very high, the centripetal acceleration is very large. Or if an object is going with some normal velocity, but it is having a very small radius, then again, the centripetal acceleration is very high, right? So where do we use this? Do we use the centripetal acceleration? Yes. The result of this centripetal acceleration, because whenever we know there is an acceleration, we know there is a force, right? So whenever there's an acceleration, we know there's a force. So F is equal to ma. Similarly, when I have A is equal to V squared over R, I know there is some F, right? And that F is given by A is equal to F by M, the same equation here. So A is equal to F by M is the equation here. And I know A is equal to V squared over R. So I'll combine these two and I can write that F, I can take this mass onto the other side and I'll get F is equal to mv squared over R. And this is known as centripetal force. A force acting on the body when it's going in a circular path and it is acting inwards towards the body. But because no such force is actually existing on the body in form of applied force, nobody is applying any force on the object, there is a resultant inertia which we feel when we go in a circular path, and this is known as pseudo force, right? So from Newton's third law, whenever there's an inward force, there's an equal and opposite outwards force, and this is known as the centrifugal force. And do we see this in daily life? Yes, almost. When you go on a roller coaster ride, even though you're upside down, you don't fall, right? You can say, sir, no, there may be they'll be putting seat belts over here, but still this entire train should fall. The train also does not fall. Why? Because it is going at a very large radius. If you take this train onto this loop over here with a very small velocity, then what happens? Small velocity means small centripetal acceleration or force, and centrifugal force is very small. And in this circle over here, the centrifugal force is outwards. Okay, it's going outwards. So gravity is pulling down, centrifugal force is pushing out, and if that centrifugal force is very small, then gravity will win, and all of these people will fall down. That is why when you go on a roller coaster ride, it goes very fast. Why? Velocity increases. And when velocity increases, centripetal acceleration will increase, or the centrifugal force will increase. And even though gravity is pulling them down, the centrifugal force is very large, and hence they'll not fall down. Right? Again, MotoGP, when I'm talking about over here, let's look at all the forces in place over here. There's the angular momentum vector is given over here, right? And because he's going on a circular path, you can see the road here is actually a curve. That's why he's bending the vehicle. The road here is actually a curve. Although he's not falling, why does he need to bend this vehicle? Because he's going on a curve over here, you have a centrifugal force to outside the radius. I mean, outwards from the radial direction. So this is the centrifugal force, this is the angular momentum, and then again you've got the gravitational force which is acting downwards, and you've got the centripetal acceleration. So because all of these forces are balanced, not only is he not falling, he's not even skidding outside, right? If he goes with small velocity and bends the vehicle like this, what happens? Small velocity means centrifugal force is very large, which means he's going to be skidding towards the side. This is why when you're bending the vehicle, while you're turning the vehicle, if you apply the brake, you're going to fall. This is because of centrifugal force. And lastly, when I'm talking about circular motions, we've got planets. Okay, I could even talk about atoms, but their physics breaks down into quantum mechanics. Not a topic that I want to discuss during this session, maybe some other time. But whenever we talk about planets, the sun, the moon, the earth, they are all going in round and round, right? So these are all circular motion. And whenever the moon is going around we know there's a gravitational force between them, and there's also moon's velocity, which is around the tangential direction over here, right? Of course, if the moon is going around the earth, there has to be a centrifugal force. So let's discuss that quickly. Between two objects of mass m1 and m2, we know there is a force, right? And this force is going to be equal, F1 is equal to F2, and that is given by gmm by r square, or gm1 m2 by r square, where r is the distance between the two objects. We call this the gravitational force, right? So whenever the moon is going around the earth, the moon is pulled towards the earth because of gravity. Of course, the earth is also pulled towards the moon, but we'll consider only the moon over here. The moon is pulled towards the earth because of gravity. The moon is moving forward with some translational velocity or the tangential velocity. That's why the moon is going forward and ultimately into a circular path. Because it's a circular path, there's a centripetal acceleration inwards. And because of the centripetal acceleration, there's a centrifugal force outwards. At any point, if this gravity is more than the centrifugal force, the moon will not remain in orbit, it will go outside. This is also true when you hold a thread, right, tied to a stone. You tie a stone with the thread and hold the other end of the thread, and you try to rotate it. What happens? When you rotate it like this, the stone will go in a circular path. You're holding the thread, right? So when you're holding the thread, there is a centripetal acceleration and the tension on the string, and the stone is pushed out because of the centrifugal force. But because it is tied to the thread, you are holding the thread will not cut and the stone will never go out. But the moment you let go of this thread, what happens? The moment you let go of this thread, the inwards force is not very much, but the outward force, the centrifugal force is much more larger, and the stone will go out and it will not go in a circular path. You'll also notice that the moment you let go of the thread, the stone will basically, like this moon, move in this vertical direction, right? This vertical direction, this tangential direction, we call it. So this is also centrifugal force. But when we talk about planets, orbits, and all these forces, we'll talk about the gravitational force, which is given by F is equal to gmm by r squared, And from this, we will deduce the velocity to go in a circular path, the angular velocity, right? But it is not the angular velocity that I'm calculating, because I know the moon goes around the earth almost in how many, about 30 days or something. So there is, the earth goes around the sun in 365 days. So they're all executed in 360 degrees in some amount of days. So we can calculate angular velocity from. But all of these objects are moving fast, and the orbital velocity can be calculated by equating these two equations. When I calculate these two equations, of course, the force acting between the moon and the earth is gmm by r square. This is gravitational force. And also I told you this gravitational force is balanced by the centrifugal force, so mv squared over r. Anytime if gravitational force is more, the moon will fall into the earth. Anytime the centripetal acceleration is more, the moon will go out of orbit. And this is not happening, which means these both are equal. And when I equate them together, r and r will cancel. There's an r squared here, so one r will cancel from here. M and m will cancel. So I can write this as v squared is equal to gmm by r. Now the moon is basically falling down. Okay, so I know v squared, so I can calculate it by square. I know the moon is falling down towards the earth basically, right? If not for the centrifugal force, if not for the orbit, moon would be falling down towards the earth, and then it would be having this force of mg, and then there's a gravitational force. So if I equate these two and cancel the m, I'll get that due to Earth's gravitational field, we've got gm by r squared is equal to the small g, which we call as the acceleration due to gravity. Right? This is 9.8 on Earth and other values on other planets. But here, what I want you to know is I take this 1r onto the other side, I will get gm by r is equal to gr. Why do I need this? Because here I've got velocity is equal to square root of gm by r. So you put gm by r as gr. So I've got orbital velocity. The velocity required to stay in orbit is root of gr. If you increase the orbital velocity, what happens? If you increase the orbital velocity, then the centrifugal force will increase. And if the centrifugal force will increase, the object will move away from the parent object. So tomorrow, if the moon starts moving at a faster velocity, then because of the velocity, the moon's orbit will face a greater centrifugal force and the orbit will become bigger orbit, right? This is why satellites, when they are set to some distance around the Earth, we need to set their velocity. Right? This is from the orbital velocity equation. And to escape this orbit, we will require to move away from the gravitational force with the kinetic energy of half mv squared, and I equate it to another gravitational energy. Right? Kinetic energy is equal to the gravitational energy. When only when these two match, I can escape the gravitational force. If my kinetic energy is less than the gravitational energy, then I cannot escape the gravitational force. So gravitational energy is given by gmm by r, and I've got the kinetic energy. Let's equate them both. I can get v squared is equal to, I've got gmm by r into this 2 will come onto this side, this m will come to the denominator. So I've got 2 gmm by mr. You can see that m and m will cancel, and I've got v is equal to root of 2 gm by r. And this is known as the escape velocity, the velocity to escape the orbit, the gravitational pull. And for Earth, if you put in all these numbers, right, g is the gravitational constant, 6.67 into 10 power minus 11. Mass of the Earth is 6 into 10 power 24 kgs, and the radius of the Earth is 6378 kilometers, so 10 power 3 meters. If I substitute this value, take the square root, then I'll get 11.2 kilometers as the escape velocity of the Earth. So to escape this circular motion around the Earth, then I need to escape from it with this velocity known as escape velocity. And for Earth, it is 11.2 meters per 11.2 kilometers per second. Right? So that is the escape velocity. So these are all the aspects covered in rotational motion. And if you consider these motion, then if you understand these motions, if you understand these equations, then all of physics, anything you learn in physics, may it be particle theory, may it be quantum mechanics, may it be some other aspects of theoretical physics, we will always and always try to convert the units into circular units, the circular coordinate system, and everything becomes easy, right? So these concepts are very important to understand greater concepts in physics. I hope it has been useful. Thank you.
ಹಲೋ ಹಲೋ ಸರ್.
ಹಲೋ. ಹಾ.
ಅತುಲ್ ಸರ್ ಹೇಳಿ ಏನಾಯ್ತು?
ಹಾ ಹೇಳಿ ಸರ್.
ಎಸ್ ಸರ್. ಯಾ ಸರ್ ಸದ್ಯಕ್ಕೆ ಕ್ವಶನ್ಸ್ ಯಾವುದು ಇಲ್ಲ ಸರ್.
ಓಕೆ.
ಏನಾದ್ರು ಕ್ವಶನ್ಸ್ ಇದ್ರೆ ನಾನು ನಿಮ್ಗೆ
Mail
ಇಮೇಲ್
ಮಾಡಿ.
ಮಾಡ್ತೀನಿ ಸರ್.
Right.
ಓಕೆನಾ ಸರ್?
Yeah.
ಸರ್ ಒಂದ್ 2 ನಿಮಿಷ ಕೊಡಿ ಸರ್. ಇವರು ರಮೇಶ್ ಸರ್ ಬರ್ತಾರೆ. ಥ್ಯಾಂಕ್ ಯು ಹೇಳಕ್ಕೆ.
ಓಕೆ ಓಕೆ.
ಅಲ್ಲ ಇವ್ರಿಗೆ ಅತುಲ್ಗೆ ಅದಕ್ಕೆ ಹಿಂದೆ ಬಂದೆ. ಸರ್ ರಮೇಶ್ ಸರ್ ಇದ್ದಾರೆ.
Professor Bhat, thank you.